Our next speaker is Matthew Scroggs. His passion is math, and we're going to speak about math and video games. And I found a very special curiosity about him, that he's even able to give some artificial intelligence to matchboxes. I don't know how he does it. It's really amazing. He even does his PhD in math, but now and today he will speak about the shortest path possible in Pac-Man, for example, and also about other video games. And I hope you will enjoy. I will. I also like very much video games and math. And yeah, welcome.
Okay, brilliant, thank you very much. Right, good evening, everyone. So yeah, I'm Matthew. I'm talking about maths and video games today. Sadly, I'm not talking about the machine learning matchboxes machine, but if you want to, we can chat about that afterwards for hours and hours, because it is really cool. But that is not my talk today. Today, we're talking about video games. And the main character of our talk today is going to be Pac-Man. And really, the title is a little bit misleading. It should say maths and video game, because I'm basically going to ramble about Pac-Man for about 40 minutes. So, Pac-Man. Pac-Man, hopefully you've all played the game Pac-Man. Just in case you haven't played Pac-Man, the aim of the game Pac-Man, you play as this character, Pac-Man, who has to go around a maze eating these Pac-Dots, while avoiding the 4 ghosts, which kill Pac-Man if the ghosts touch Pac-Man. And Pac-Man starts in the maze like this. So the aim of the game is, you start here, you go around the maze eating the Pac-Dots, and once you've eaten all the Pac-Dots, you get to go to the next level. OK, so as a mathematician, I play this for a little bit, but then I kind of start thinking as a mathematician and start wondering, what's the best way of doing this? What's the shortest path I can take? Or possibly, can I do it without having to double back on myself? If I could do it without doubling back on myself, it would be very, very nice, and I could do it very quickly. So this is related to a very famous mathematical problem called the 7 Bridges of Königsberg. So this is a map of Königsberg, which is a town in what is now Russia. And on the map, you can just about see that there are islands like this with 7 bridges shown in orange here. And the story goes that the townspeople of Königsberg used to spend their Sunday afternoons starting at their house and trying to walk around the island, crossing each bridge exactly once. So very similar to the way Pac-Man wants to go down each road exactly once, the townspeople try to go across each bridge exactly once. So for example, they might go around here, keep going around there, and now they have found that they are stuck and they have missed out this bridge here. So that is not a solution to the problem. So they tried this for a very long time, and they found it really, really difficult to manage a path where they went over all the bridges exactly once. And eventually, this man, Leonhard Euler, came along, and he proved that actually the reason they were finding it so hard was because it is actually impossible. And he explained why it's impossible, and invented a whole new branch of maths called graph theory, from this problem. And the way he proved that it was impossible, and this is then going to be useful to apply to Pac-Man, was by realizing that, first of all, the map and the way everything's laid out is kind of unimportant. What you can do is you can represent each island with kind of a point, and then replace the bridges with lines between these points, something like this. And then we can ignore the map completely, and that smaller diagram here has all the important information. It shows us there's 4 islands, and this is how they're connected with bridges. So now, instead of imagining us walking around the islands, we can imagine that we are walking around the lines in this graph. OK, so now imagine we are thinking about just one of the islands now, and it's got some combination of bridges going out of it. Here we've got an even number of bridges, and the nice thing with an even number of bridges is that if you come into the island, you can go off the island again, and if you come in again, you can go off again. And if there's an even number, every time you come in, there's a pair that you can go off in. Whereas if there's an odd number of bridges coming onto the island, then we can pair up the other ones, and then we're left with 1 bridge left. And now if we come off the island, we get stuck on the island. So that is, if we have got dots and there is an even number of bridges going off the dots, we will be fine, because every time we come on, we can get off again. But if we have an odd number of bridges going onto an island, we're going to get stuck on the island. So that means that if we have islands with an odd number of bridges, we are not immediately screwed because we can always end there, or we can start there. But if there are more than two bridges with an odd more than two islands with an odd number of bridges, then we are not going to be able to do it. Okay, so back to the Königsberg graph. You can see here that we have got 5 bridges, 3 bridges, 3 bridges, 3 bridges. We've got 4 islands with an odd number of bridges, which means that we are going to get stuck on all the islands at some point, so we cannot get around this graph without going over an edge more than once. Which means that it is impossible to walk on Königsberg going over the bridges exactly once, and this is what Euler proved. Okay, so an interesting aside at this point. So during the war, Königsberg was bombed. It's now called Kaliningrad as well, and it now looks something like this, and now has less bridges like that. So now we can solve a different problem, which is the 6 bridges of Kaliningrad, which has a different representation, which looks like this. So you can see the bridge that was here has been destroyed, which is going to help us, and there's also a new bridge that's been built down here. And now, now you can see that there are 2 islands with an even number of bridges and 2 islands with an odd number of bridges, which means that now, if you're going to go on holiday to Kaliningrad, you can actually do the walk going around each island, or going over each bridge exactly once, as long as you start on one of the odd islands and end on the other odd island. For example, that route there will get you around all the bridges without going on any bridge more than once. Okay. So that is the related mathematical problem. Now, let's go back to Pac-Man. So we want to apply the same thing to Pac-Man. We want to look around our Pac-Man route, and we want to see if there are any islands, and the islands are going to be kind of the junctions, like here and here and here, where multiple routes meet. And we want to see if any of them are odd. And if you kind of look around, you can see there are an awful lot of places where there are an odd number of roads coming in and out. If we change it into a graph, all the ones colours in red are odd. So the bad news for us is that for Pac-Man, it is impossible to complete Pac-Man without doubling back on yourself, which is perhaps not too surprising. If you've played Pac-Man, you will know that you cannot kind of really go around it and not have to double back on yourself at some point. So it's not particularly surprising, it's impossible. Right. So we've found out that it's impossible to complete Pac-Man without doubling back on ourselves. But there's more to this question that we can still ask, because we want to know now what is the shortest route we can take to complete Pac-Man. There's going to be some doubling back, but how should we do this doubling back to make the route as short as possible? And for this, we need to talk about what is called the Chinese postman problem. So this is a problem, again, that is older than Pac-Man. And the idea here was that you have a graph, something like this, and now you have a postman who wants to travel around the graph, and he needs to go down every street to post letters. And the question is, which road should he go down more than once in order to make the shortest walk possible while delivering all the letters? And the way you can solve this problem, if, looking at your graph, if all of these were even numbers, so if every island had an even number of bridges coming off it, every vertex has an even number of edges coming off it, you would be fine because you could go without repeating. But when you have odd vertices, when you have an odd number coming out of any of these nodes, then those are the ones you're going to have a problem at. So what we can do is if we take all the odd vertices in pairs and match them up, and like this, so where I have doubled up an edge, so here and here, I'm kind of saying, doubling up an edge is like saying I'm going to walk down that street twice. So if we change the graph to that, we can now walk around that without going back on ourselves, except we are secretly going back on ourselves down these edges that we have doubled. But we don't know that's the best way of doing it. And actually, for 4 odd vertices, there are these 3 different ways of pairing up the odd edges. This one even gets more complicated because there wasn't actually a road going from this island to this island, so you'd have to go via one of the other islands, which is a sign that this probably isn't going to be the best solution. So, to solve the problem, what you would do is look at all these possible ways of pairing up the edges, sorry, pairing up the vertices, and then look at which one you've added the least amount of distance to, and that is the one that will give you the shortest path. Okay, so we can take this idea and we can throw this back at Pac-Man and work out what the shortest path is. There is a slight problem, but we're going to get over it, that as the number of odd vertices increases, the number of pairs that the number of different pairings you have to check increases quite quickly. So if we look at Pac-Man, if you count those, there are 20 red circles, I believe, which means that to solve Pac-Man, we're going to have 654 million different ways of pairing up these edges to find the shortest one, which is quite a lot. But I left my laptop going for a couple of days, and it managed to solve it. So for this problem, there are actually faster methods you can use to solve this, but this wasn't a big enough problem that I bothered implementing them. So you can do it slightly faster, although it still increases quite quickly as you add edges. And I found that for Pac-Man, to complete it in the shortest possible amount of time, these are the edges you should repeat. So you can see now that every place where we had an odd number of lines coming into it, we have now chosen something to pair it with. So these are the edges that we should repeat. So if the slides work, we should now have a video of me doing exactly this, hopefully with sound. OK, so that was the shortest route I could take to finish a level of Pac-Man. Except some of you out there might have noticed that there's actually a few problems with this method so far. And we can actually do slightly better. So there are a few points, most noticeably up in that corner up there, where I went a little bit too far and turned around a little bit too late. And that was because I was playing with my stupid human reaction times, and I was quite slow. So if I did a machine-assisted tool run, I could totally do it slightly faster. But there are a few other problems that are a little bit subtler that we need to deal with in order to actually do the fastest level of Pac-Man possible. So now we're going to look at some small parts of the map and see what is the best thing to do at some small parts of the map. So the idea is that we want to double up all of these little routes, but we now need to decide which order to do them in, because there are some slight improvements we can make. So the first one, if we have just a standard old corner. So if we take screenshots kind of frame by frame, and you press down in this frame, then it will take this many frames to get around that corner. Whereas if you press down one frame later, it takes one extra frame to go down, which means that every time you do a corner, you need to press down in the exact right frame. Luckily for us, if you just hold the down button, this is the frame it will move down in. So if you play Pac-Man by holding the arrow key before you get to the corner, you are doing it in the best way possible. So the corners are actually quite easy to get perfect. OK, let's look at one other situation that can happen if we want to go straight on across a straight line. So you might think that this is really the only way of doing this. You just let Pac-Man go straight on. But actually, there is a slight improvement you can make here. Because when you turn a corner, Pac-Man goes sideways quite quickly. In fact, if you press down in that frame there, and then press left again in that frame there, Pac-Man totally skips out one frame of movement. So that is if you go straight on, and if you do a kind of like nudging downwards, you skip one whole frame. And the game runs at 60 frames a second, so you've just saved 1/60th of a whole second to slightly speed up your time. OK, and there are some other situations we can look at. Like we can look at if we've got a crossroad, we can do this one or this one. And the two corners is going to turn out faster if you look at the ways you do them. Oh, as well, I should have mentioned, interestingly with this one, if you're going upwards or downwards, this trick doesn't work and actually slows you down. So you want to only use this trick if you're going horizontally. OK, now, so if you've got crossroads, yeah, it turns out that this one is faster, even if you use the slight speed up trick there. So whenever you've got a crossroads, you want to try and corner twice rather than going straight on twice, because you can see that going around the corners twice takes 50 frames, whereas going straight across takes 57 frames. We're talking large fractions of a second here, which is very, very important. Similarly, if you've got this kind of thing here, so you've got a T-junction and another T-junction, this one lets you skip out actually almost like a second's worth of movement here by not going over that bit twice. So we want to try and do that if we can and avoid this one. And we can look at other situations. So here, it turns out that one is slow, and these two are almost exactly the same. I think they are actually exactly the same. And by analyzing all the different positions in slightly more detail, we can now find that this route here is the route we want to take to do Pac-Man in the fastest way possible. So we're repeating the same edges as I said before, but we've now ordered them in a way so that you can see all the crossroads have 2 corners in them here and here. We're turning around in the right places there to make it as fast as possible. So this is the route we want Pac-Man to take now. So hopefully there is another video. Yeah, so we have a slight problem here that now that we have fixed a lot more, so there's a lot less, when we looked at before and I just said which edges I wanted to repeat, there are a lot of choices for where I could go, whereas here, there are only about 4 or 5 different routes that take all the best options possible. I tried them all, and I could not find a way of doing it without bumping into a ghost. So I gave up. So I am actually not sure what the fastest way of completing a level of Pac-Man is, so my talk description was a lie. I don't know how to complete Pac-Man the best way possible. This is how I want to do it, but I need to find some compromise between this and the other one that will be quite fast. For that, I need to work out how the ghosts move, but that is going to be something I'm going to come back another time and tell you about. We're going to go on now and think about another thing that happens in Pac-Man. So I hope everyone as well has played Pac-Man and is aware that if you go off here, you magically appear over here and come back on the other side, like so. And this might seem a little bit weird because we're used to living on a flat surface. But actually, we can think about this is not actually weird behavior at all if Pac-Man was living on a cylinder. Because if we take the Pac-Man surface and wrap it round, then Pac-Man is just kind of going round and round the cylinder, and it makes perfect sense that this kind of behavior would happen. Another video game this happens in is the amazing Bubble Bobble, where if you take Bob off the bottom, you fall back on the top. Although with this one, weirdly, you can't then jump off the top again and come on the bottom. But again, we can imagine that this game is taking place on a cylinder, this time the other way round. OK, and this, again, ties into a fairly famous mathematical thing that you can do, which is to take a bit of paper and kind of imagine folding it up and see what surfaces we get. Excuse me. So I'd like to imagine that you have got a nice big flat sheet of paper, and this paper is slightly stretchy, so we can kind of bend it if we need to later. And what we're going to do is we're going to label edges of this paper and imagine wrapping it up so the arrows line up. So I'd like to imagine this is a piece of paper, and you want to bend it round so that these 2 arrows line up and face the same direction, and imagine what shape that's going to make. And hopefully you won't be too surprised that if you bend this round, you're going to get a cylinder. So this is very much, this is what Pac-Man does, is Pac-Man goes off one side, and he comes back on the other side, having not turned upside down, and we wrap round and get a cylinder. Although actually, in fact, I guess Pac-Man couldn't really tell if he was upside down, so maybe it could be the other way up, but that is a cylinder. If it is the other way up, so I'd like you again to imagine that you're taking this paper, you're wrapping it around, but this time there's a bit of a twist in it. So here you need to use the fact I said that the paper is a bit stretchy. With actual paper, you're just going to tear the paper, and it's going to be really messy. But with stretchy paper, you're going to bend it round, and you're going to get a shape like this, which is called a Mobius strip. If you've not played with Mobius strips before, I recommend going and playing with Mobius strips. One really fun thing to do is if you try and cut it in half, imagine like you try and make 2 Mobius strips, so cut one in half. You'll be very surprised to see what happens. Another great thing you can do is if you get 2 of them and glue them together, then cut both of them in half, really, really strange things happen. So that's something for you to go and play with there. But of course, we've so far only labeled 2 of the sides. We could label multiple sides. So here, I'd like to imagine, again, before I show you what's going to happen if we bend this paper around to fold it up. So we're bending it round. Again, it needs to be stretchy. And we're not going to kind of fold it flat. We're going to leave some space inside it. And this one, you can kind of see that it's going to make, if we squish it about enough, it's going to make something like a sphere, with a lot of kind of bending and stretching and flattening, some sort of 3D shape like a sphere. OK, here is another one. So another way of labeling the sides. Here again, I'd like to imagine what's happening before I show you. So you're bending the red arrows kind of make it like a cylinder, and then you're connecting the top and the bottom around again, and you are going to get a donut or a torus, is hopefully what everyone is imagining. We're going to come back to this shape very shortly. I'm just going to show you a few more interesting mathematical shapes first. In fact, perhaps you can think of a game that is going to become a torus very shortly that has this kind of relationship going on. And you can make more interesting mathematical shapes. So this one is a lot of mathematicians' favorite shape. And I'd like to again imagine what happens. So again, if you take the red arrows, you can see it bending around in a cylinder. And now we're kind of doing like we did before, except you've got to kind of like pop the other bit upside down as you make it into a donut again. And you're going to get, in this case, what is called the Klein bottle. So you can see here, you got the cylinder, you tried to bend it around, and then you kind of had a big problem here where it went through itself. So this is actually a four-dimensional shape here. In our normal three-dimensional world, that can't happen because the shape can't go through itself. But in 4 dimensions, you can kind of imagine that there's enough space in the extra dimension to kind of like bend it around and go back inside itself. So by simply telling you how to fold up 2D paper, I've already made you make a 4-dimensional shape. And we're not limited to just folding up squares as well. You can fold up more complicated things. This is one I cooked up, which looks difficult, but actually if you notice, those top 4 are actually just the same as the torus or the donut I showed you, and these are the same as another torus or donut. So maybe not so surprisingly, it folds up to make a double donut. And in fact, you can make an awful lot of different mathematical surfaces like this, and it's a big area of interest in maths that you can use this method to describe the properties of surfaces quite well, and it's actually quite useful. OK, back to video games. So hopefully when I said if you're thinking of a game that would work like this, some of you may have thought of Asteroids. So we all know that if you play Asteroids, so this is where you play as a little spaceship, and you move around kind of shooting the objects. And if you go off this side, you magically come back on over there. And if you go off the bottom, you magically come back on the top. So we can imagine that it works like this. If you go off the sides, we're kind of going to want to bend those round so they fit together. And top and the bottom, we can bend those round so they fit together as well. So just like we saw when imagining our abstract paper, the game of Asteroids is going to bend round and bend into a torus, something like this. So if you've played Asteroids and think it's some kind of lame 2D game, you were wrong. It's actually an amazing 3-dimensional game. But there is a problem still with Asteroids here. And anyone that's played it will know that if you go upwards in any of these 3 directions, these are the same length. Similarly, if you go across in any of these directions, these are also the same length. But if we map it onto a torus, like we've done, if you bend it into a torus, because we've done some stretching, this loop around the middle is an awful lot smaller than that loop around the outside. So if this was what Asteroids looked like, it would not behave in the same way as possible. The spaceship would move faster towards one end of the screen than the other end of the screen, which is not how Asteroids behaves. So we need to think a little bit more carefully about what shape Asteroids is going to look like. And to do this, I would like you to imagine, if I go back a slide, taking one of these directions. So we're going to kind of bend it around one way and imagine just one of these lines. So as we bend it around once into a cylinder, we've not stretched anything to go to a cylinder, which means that everything is still going to work, so that we're happy with a cylinder. And each of these lines is going to fold around into a circle. So I'd like you to imagine one of these lines which becomes a circle. We're now going to move that circle, not like this, in a different way. And the next slide takes a little bit of time to load. So bear with my computer. Here we go. So we're taking that circle, and now we're going to move the circle like what is going to happen now? It's going to move it around like this. So what we're doing is we're taking the circle, and we are spinning it in a loop without rotating the circle. And now, if you look at different points on the circle, each point on the circle while going round is taking the same amount of distance. Because we're not rotating the circle at all, each point moves by the same amount as we go around this circle. Which means that if we look at the shape that this circle traces out as we move it around, this will represent Asteroids, because at every point on the loop, our directions in one way are going to stay the same length. And our directions the other way are also all the same length, going this way. So let's trace out the shape and see what we get. Go something like this. We get this shape. And hopefully, as you go around, some of you are going a little bit cross-eyed about that point. and the same point at the bottom, because it is actually going a little bit weird there if I just put the whole thing up. What happens is it's all looking fine until at this point at the top and this point at the bottom, where the circle kind of passes back through where it's already gone somewhere before. And that is because this shape is impossible in 3 dimensions. So just like the climb bottle I showed you a short while ago, you cannot make this in 3 dimensions, because as you go down the bottom, the shape then has to kind of cut through itself again, which is why our normal torus doesn't have this nice property of having the same distance everywhere. So again, this is a 4-dimensional shape, because in 4 dimensions, you have that extra bit of space. You can just kind of take it into the 4th dimension, round itself, and then put it back there. So we have just worked out that Asteroids is not a rubbish 2D game or a rubbish 3D game. Asteroids is actually an incredible 4-dimensional game, and probably the first 4-dimensional game. Which is surprising, because it seems like it's kind of 2-dimensional and boring. But Asteroids is definitely played on the surface of this 4-dimensional torus. OK, there are some other games that are played on 4-dimensional toruses. One of my favorite games ever, the Final Fantasy series. This is the map from Final Fantasy VIII. Anyone who's played it, when you get to the world map, will know that excuse me, when you get to the final disc and you've got kind of the spaceship, you can fly off the top and come back on the bottom, and you can fly off the side and come back on that side. Just the same as Asteroids, which means that, again, you could label it like this, just like we did, and you will get the torus. But again, because we know what we know about Asteroids, because all the lines this way take the same amount of time to go across, and these lines take the same way to go across, Final Fantasy VIII and all the other Final Fantasy games on the PlayStation 1 were all also played on the surfaces of a 4-dimensional torus, which makes it super embarrassing when you look at this screenshot and they've drawn a sphere, which is entirely incorrect, and you should all write to the game developers and complain. OK, so that is where I'm going to leave you today. Thank you very much for listening. I think I have some time for questions.
Thank you very much, Matthew Scroggs. So there's still some time left for Q&A. Please queue here, or on the other microphone in the back. Like, you can stay here.
OK, so with your graph representation of the Pac-Man map, you did not add edges for the paths that didn't have dots.
Yes, let me go back.
But it looks like, at least in one instance, it would be quicker to take one of those paths than to backtrack through 2 other paths. So have you thought about doing that to maybe find a quicker way?
So you're saying, you're probably looking at this one here.
Yes.
It looks like it's shorter to pop down there, which is I haven't included in the graph I showed you here, where I have, I've left those 2 detached.
Yeah.
So yeah, I did look into that. The problem you have is if you connect those 2 up, if we go, it's a long way forwards. There we go. Whoops. Look at this one. If you connect those 2 up, you end up being left with having to connect kind of like this one of the ones over here with one of the ones over here. So what looks there like a good idea means you have an odd number of nodes over there, an odd number of nodes over here, and you have to have a long one going all the way across the top, which ends up ruining that being a good idea.
OK, but like there might be another one of those paths might be quicker. Have you actually proven that this is the case for all these edges?
So I went through every pair and looked at all the different routes between. Taking every pair, looked at all the shortest routes, all the different routes between every route, and found the shortest one. So I think I have done that, but I may have made a mistake.
So, any more questions? We have still a lot of time left. You were very fast.
Yeah,
really running through your slides.
I'm ready to go to bed. It's late.
OK, so thank you again. And
we have a late question.
oh, there's another question.
Yeah. Hi. I have a question about asteroids. Why is it specifically a 4D torus when it looks like a sphere could work just as well? So if you could explain this to us mere mortals, that would be great.
Yes, sure. Where's the asteroids picture? Down here. Okay, cool. Put the picture up there. Okay, so the idea is that with asteroids, because when you go off the side, you come back on the other side, that means that when folding this into a shape, you kind of have to take this side here and kind of fold it around so it matches up with that side. And in that way, you're going to get a cylinder, like a tube. But now, because the top and the bottom, which have now been wrapped into circles, when you go off the top, you come back on the bottom, you've got to bend it around so those two circles touch each other, which means that you've got to take your cylinder and kind of bend the ends around to go together. If you made it a sphere, then, like, if you imagine this was a map of the world, when you go off the top of the Arctic on the world, you don't come back on at the Antarctic. And that'd be the problem. If they wanted asteroids to be on a sphere, you would have to go off the top and come back on a different part of the top. Because you can't draw any map of the actual world where, like on the actual world, you do go off the side and come back on that side, but you cannot ever go off the top and come back on the bottom, which is what leads it to having to bend around into a torus. Okay, we can talk afterwards if you like, and I can draw some pictures.
So, but
really
that basically means if you keep the distance the same, but you would automatically speed up the ship when it goes through these. When you change because asteroids only had one speed, like go and stop, basically. If you would adjust the go speed to the place on the map, you could make it a three-dimensional game again.
Yes,
by just sort of
definitely.
like taking space and folding it a bit, but keeping it spatially the same, if you know what I mean.
Yeah, so you could definitely represent it flat. Again, just like the planet Earth, if you kind of run around the equator and run around the North Pole, you get very different speeds on the
And it
map.
would be kind of fun. I would like to see what they would do to the game dynamics.
Yeah, if anyone here wants to program asteroids for the badge, please make one that's actually on a sphere.
Yeah,
I would love to play asteroids on a climb bottle as well, where you go off one side and come back, and then if you go off the top there, you come back on here, so you're actually playing on a climb bottle.
Right.
That would be really cool.
Okay, thank you. Lovely talk. Thank you so much.
Thank you.
So any more questions? Oh, there's another one.
So what ideas have you got for how you can account for the ghosts in not computing the optimal Pac-Man solution?
So the first thing I need to do is I need to read up on what the ghosts actually do, because they do follow predefined patterns. And if you work out what the ghosts are going to do, you could plan the route while at the same time planning where the ghosts are going to go, and kind of make your decisions of which thing to do based on where you know the ghosts will go next, and try and work out a short route that avoids the ghosts. I think it's going to be a lot of work, but hopefully in 4 years' time I can come back and show you the video.
You don't necessarily have to avoid the ghosts if you can get to the big dots before meeting them.
Yes, and actually that was one of the problems I had trying to do it. Oh, that's weird. I'm just scrolling up and it can't deal with it. I'll stop now. Yeah, so the problem I had with the dots was when you get to this dot, so I have some I didn't take a video of where I managed to get slightly further. The problem is, from there, you have to go all the way around the top, all the way down here, all the way around that top, all the way down here, and all the way up there. And there's no other way of doing between that big dot and that big dot. That doesn't take in all of that route there, and that is way too long that one the ghost always gets you along the top if you do the perfect route. So I reckon to do it, we need to make some adjustment at the top so that those dots are slightly closer together in time, because there is just too much distance at the top.
Okay. Please go a bit more close to the micro. It doesn't work.
Okay, no, this is better now. So even though this particular attempt didn't work, presumably this gives you a lower bound of how fast you could do it. So what is actually the margin between this lower bound and the upper bound that you did find?
That is a very good question. I've totally not counted the number of frames it takes. I come find me tomorrow and I will work that out for you. There's probably not very much in it. Like, most of the improvements I've made are a few frames here and there, so it's probably like less than a second in it. So we're not far off doing it perfectly.
you.
So any more questions? We have still time left. Yes, there are.
Would it be possible to calculate gravity force between two asteroids analytically?
Of calculating what, sorry?
Can you please go a bit closer to the micro? Louder.
Is it possible to get the gravity force between two asteroids analytically?
Probably. I haven't done it, but I wouldn't be surprised if you could. Talk to me at the end and we can see if we can work it out tomorrow or something.
So one more question, and then I would close the line for the day.
You mentioned with Bubble Bobble that one could go down the openings in the bottom and you'd then fall onto the screen from the top. You also said that you can't then jump up from the top and appear at the bottom. But have you tried blowing a bubble and bouncing on top of the bubble to get the extra heights? And I think you might be able to come up through the bottom at that point.
Can you? In that case, I'll take back everything I've said about Bubble Bobble, and it's way deeper than I thought it was. So that simply means that I guess that this distance here is probably just larger than I gave it a count for there, and I just need to expand that distance, and then it will be accurate. Thanks. I'll change the slide.
Okay, thank you again, Matthew Scruggs.
Thank you.
It was a beautiful talk. Thank you.